Welcome to the week 8 of NPTEL course Introduction to Mobile Robotics. I am your TA Suraj Borate from IIT Gandhinagar. I am PhD student and a PMR fellow. And this week, since no one has joined yet, we are actually just going to, so there won't be any doubt solving, but uh, we will try to revise questions from all the weeks because we have already completed all the week assignments. Uh, so we will just revise some questions from all the weeks. And if you have any more doubts, reach me through email ID. My mail ID is surajb@iitgn.ac.in. Okay, so let's start. Given a differential ride robot which localizes itself in work environment using odometry. So odometry, as you know, is the way of finding the position of the robot through integrating its uh, commands step by step, right? Okay, so the odometry is based on wheel sensor readings. So there are wheel encoders depending which are like disk, and there are slots, and when the light passes through the slots and is read by the light sensor, then you understand that okay, one slot has moved, and so the entire has let's say 10 slots. Then when 10 slots move, we say that there is one rotation of the disk. Okay, so select the deterministic errors that can be eliminated by the proper calibration of the system. Okay, so when we say calibration, it means that we look at the errors, and whatever we see that uh, whatever errors are there in that, what the at least the deterministic part, like when we say deterministic, it means that there is some logic to it. It's not completely random, and there is a reason, and then or the cause. There is a cause, and then there is a effect. So that is called as deterministic, and these can be eliminated using proper calibration. That is true. And so, what are those? So, uncertainty in wheel diameter. Obviously, we can measure the wheel diameter, right? And in particular, unequal wheel diameter, right? Variation in contact point of the wheel. Okay, so that is not something in our hands. It's very hard. It's very stochastic. So that is not that doesn't fall under deterministic, right? Misalignment of wheels, yes. So the thing is, option B and D will cause a same pattern in the error to happen, right? And that a pattern can be identified and eliminated, or that is what is called as calibration. Okay, let's move on to the next question. For a differential drive robot, initial pose is at A and it is given, and then at B, it moves to B. Given the distance between two wheels is so the L value is given as 2L value is given as 1, and right and left wheel transfer distances are given. So left wheel travels 3, right wheel travels 3, and left wheel travels 2.5 units. So what we have to do is just calculate the delta S. Delta S is given by delta SR plus delta SL by 2. So 3 plus 2.5 by 2 is 2.75. So such questions can be expected. And then the next, what we have to find is what will be the change in pose from A to B. So when we say pose, it means that the X and Y position along with the orientation, right? So this is the formula. Delta theta is nothing but delta SR minus delta SL by B. So when you substitute that, you get the answer. And delta X and delta Y can be given as delta S cos theta plus delta theta by 2. So this comes directly by the trigonometry. Okay, delta S. And when you substitute this, you get this answer 2.49, 1.17, and 25. Okay. So this is just application of the formula. Okay. So for given input velocity command, find derivatives of generalized coordinate known as inverse differential kinematics. Okay, so as we know that forward differential kinematic equation is given eta dot is equal to j of psi into zeta. So zeta is the input velocity command. If we give input velocity command, then we get the generalized coordinate. What is generalized coordinate? X, y, and psi. Okay, dots. So this is forward differential kinematics. The inverse is like when you take J inverse and send it to that side. Okay, so like multiplying both sides by J inverse, you get this identity. So you don't have to write the identity over here, right? So that is inverse dynamics, inverse differential kinematics. Sorry. Okay, so let's move on to the next question. Okay, this is something that you can expect. X dot y dot psi dot is equal to j into zeta, right? So we have this expression and it is given as zeta value is given and 90-degree is the orientation. So just substitute in the formula and you get the answer. Okay, so this is the when you multiply you will get 0 1 0. So this is the generalized coordinate rates, right? Very important, the sign minus sign, not sign minus sign is not here, it's here. Okay, that you should remember. Okay, for a conventional car or van, the degree of freedom. Okay, what are the degree of freedom? X, Y, and theta, right? And the degree of maneuverability is what? Okay, so degree of maneuverability is nothing but degree of mobility plus degree of steering, right? So for a car, the steering is one and the mobility is one. Why mobility is one if there are two wheels? Because they are driven by the same axle, right? Only one engine is there and it is driving both the wheels. So one plus one, two. This was a trick question. So you can expect something like tricky questions to come in exam. Although I don't know exactly what comes in exam, so I don't. But I have chosen some questions that I found tricky through all the weeks. But yeah, you have to study everything, and I don't know what will come. Okay, so all the best for that. But let's move on to the next question. Asymptotically stable means what? So when you say stable, stable means bounded input gives bounded output, right? So the output should be bounded. So we are assuming it's a linear system, and for linear system, this definition is good. Bounded input gives bounded output, but uh, okay, here is something I will like to share. So for a second order system, do you, do you know if there is some bounded input that can cause unbounded output? So okay, so like the hint here is resonance. Okay, so certain frequency can cause resonating behavior. Okay, so okay, let's forget that. And the question is like asymptotically stable. So when you say asymptotically stable, the output converges to certain value. Okay, and it's not just bounded, but it actually converges to a value as time goes to infinity, right? So the answer is as time tends to zero, sorry, to infinity, the tracking errors tend to zero. Okay. Okay, so second order aerodynamic stable as per the following condition. Okay, so this is the condition. Okay, okay, the symbol, I don't know what to call it. Maybe it's gamma 1. Let's call it gamma 1 and gamma 2 uh, should be greater than 0. Why? Because when you put the greater than 0 sign over here and the solution is in the form of exponential, reducing exponential, which is nothing but asymptotically stable. uh, Eta, right? So that is what we want. Or you can say the eigenvalues will be negative for this system if you represent it in a state space form. Okay, so the vector of input commands or the control inputs of a computed velocity control is given as, so this is another important question. So you can see that it is J inverse eta into eta d dot plus J inverse lambda into eta. Okay, so there is a feed forward term and there is a feedback term. Okay, so that is very important. So there is this eta d dot is nothing but the feed forward term, and lambda into error, that is eta tilde is the error term. So that is the sum of feed forward and feedback terms. Okay, this is another type of question that we can expect is from the sensors week, is like what is exteroceptive and uh, what is the proprioceptive sensor. So exteroceptive measures the outer data, and proprioceptive measures the data which is inside or related to the robot. And just follow this table. This table is very good. Active, passive, and exteroceptive, proprioceptive, all types of sensor are covered over here. So thank you. I stop here, and all the best for your exam.